Olá pessoal, muito bom dia a todos e a todas. É com grande prazer, então, que hoje a gente retorna no nosso último dia do 5º workshop de computação quântica da UFSC. Então, lembrando que hoje nós vamos ter o mini curso da Guanru Feng. Ela faz parte da SpinQ Computing, uma startup de tecnologia quântica da China. Ela vai falar hoje para a gente, então, sobre computador baseado em ressonância magnética que eles desenvolvem lá na empresa e que também é um computador que serve para fins didáticos, onde pessoas que não sabem como funciona um computador quântico vão ter a oportunidade, vão poder programar um verdadeiro computador quântico. Esse computador quântico é computador portátil, além de outras opções que eles têm dentro da companhia deles. Contudo, como ela vai falar inglês, agora eu vou mudar então para inglês. Hello everyone, welcome to the last day of our 5th workshop on quantum computing. Today is a great pleasure to introduce you Guanru Feng from SpinQ Quantum Computing. Let me introduce you Guanru right now. She's PhD in physics by Tsinghua University. She did postdoctoral research in IQCU and a quantum-device research technique in University of Waterloo. Currently, she's senior scientist at the Shenzhen SpinQ Quantum Technology Company. Guanru, okay, yeah. Welcome. Thank you for accepting our invitation. It's a great pleasure if you're here. The time is now. Good course. Okay, thank you.
Thank you very much for the invitation. It's an honor to do the mini course here. So let me share my screen. So I will stop the camera for better connection. Stop share screen. Is my screen there? So let me see. Oh, here. Share screen. Can you see my screen?
That's right. It's working.
Yeah. Great. Today my topic is NMR quantum computing and the desktop quantum computing platforms. I'm from SpinQ. So SpinQ is a quantum computing company in China, and our product includes NMR desktop quantum computing platform and also superconducting qubit systems. So today I will mainly focus on NMR desktop systems. So this is my outline. So first, I will talk about why we need to consider quantum computer. Then is the basics for quantum computing. But I will also give a quick introduction to different physical systems of quantum computing. And finally, I will talk about NMR quantum computing and the SpinQ products. Then why are we trying to build quantum computers? Why are quantum computers attracting more and more attention? So first, let's take a look at the computers we are using every day. This is a motherboard. So the central part is a CPU. CPU, there might be hundreds of millions of transistors. So transistors are the most basic unit of a CPU. So transistors have multiple ports. So usually it has a base port. So it acts as a switch. So if the base port is provided with a low voltage, there will be no current through the other ports. So if the base port is provided with a high voltage, so there will be current through the other port. So control voltage high and low, the two states are used as one bit in classical computing. So by using the properties of transistors, basic logic gates can be realized. For example, connecting two transistors in series, it can realize the add logic gates. And if connect the transistors in parallel, so it can realize all gates. And by using those basic logic gates, more complex gates can be realized, for example, addition, multiplication, etc. So from those transistors, those very basic units, so computers of different uses are built. Even the most powerful superconductors nowadays, they are built from these small transistors. And the engineers and the scientists are still working on improving the performance of today's computers. So they are more and more powerful every day. However, so due to physical limits, their performance won't improve without a limit. So the Moore's law says the number of transistors on integrated circuit double approximately every 2 years. So this also means the sizes of transistors are getting smaller and smaller. So the size scale is approaching nanometers. So at such a small scale, the quantum effect is beginning to dominate. So for example, we hope the transistor to work as a switch. But at such a scale, when the base port of the transistor is provided with a low voltage, so that means we want no current through the other port. But quantum tunneling can happen. So that means the quantum tunneling of electron may cause a current. So that means this switch doesn't work well anymore. So this is a limit of the size of the transistor. Another problem to have more and more transistors on a chip is the heating problem. So it's very difficult to efficiently remove the heat away. So the heat is generated by transistors on the chip. So it's very difficult to efficiently remove the heat. So that's another problem to having more and more transistors on a chip. So that means the performance of the CPU will be limited. But more powerful computers are still demanded by people. So there are many situations where today's most powerful supercomputers seem not powerful enough, both in scientific research and in people's daily life. So here's one example. In medicine, material science, biology science, etc., simulations of large molecules are needed. So however, classical computers cannot simulate the complex microscopic world. So this was the very reason Feynman came up with the idea of quantum computer. So to use quantum computer to simulate the quantum world efficiently. So then what is quantum computing? First, let's know something about quantum mechanics. So quite different from Newtonian mechanics. So quantum physics was established by work of a group of talented people. So maybe it's because quantum mechanics is so counterintuitive. Repeated discussion, dispute, brainstorm were necessary for it to establish. Quantum mechanics is the rule that the microscopic world obeys. The microscopic world include atoms, electrons, photons, and the Newtonian physics does not apply to such small particles. So let's use the hydrogen atom as an example. The electron in a hydrogen atom has different energy levels. So those levels are discrete, so not like the case of satellites around the Earth. And for each energy level, quantum mechanics does not predict the exact location of the electron. It only predicts the probability of finding it at a different location, at different locations. So here is a picture of different orbits of the electron. The brighter places represent a higher probability of finding the electron. So after people had a better understanding of the microscopic world, new technologies emerges. So it includes transistors and semiconductors, also the laser technology. So this is called the first quantum revolution. First quantum revolution includes means observing and understanding the microscopic world, and also after understanding is to make use of the microscopic world, make use of different effects of the microscopic world, but it does not include actively manipulating the quantum states. So second quantum revolution is happening currently. Is understanding of deeper manifestation of the quantum world, and it includes actively manipulate quantum state and sometimes customize quantum systems. So the technologies include quantum computing, quantum communication, and quantum sensing. So quantum computing provides with quantum speedup. So some quantum algorithms can provide exponential speedup over classical computing. Quantum communication provides secure communication. Quantum sensing provides high sensitivity in sensing. So quantum speedup is because there is quantum speedup because of special very special properties of quantum particles. They are superposition and entanglement. Superposition means a quantum particle can be can be in different state at the same time. So the superposition can provide a quantum parallelism. Entanglement is a kind of non-local correlation between quantum particles. It's non-local, that means the entangled particles, if they are far away, the correlation still exists, and operate on one of them will have simultaneous effect on the other. Quantum entanglement is widely used in quantum communication. And this year's Nobel Prize was awarded to those pioneers who demonstrated quantum entanglement in experiments. Quantum computers have been proved to have speed up over classical computers in some problems. So the most famous two are the prime number factoring and the unstructured database search. So those two problems are the most famous and also were the earliest studied problems in quantum information. Nowadays, more and more quantum algorithms have been for example, the HHL solving linear system equations. So this algorithm solves linear system of equation. And there are a lot more. So if you are interested, you can search on the website Quantum Algorithm Zoo. So first I will quickly introduce the factoring big number algorithm. It was proposed by Peter Shor, and this algorithm is named the Shor algorithm. So it's about the RSA encryption is widely used for secure data transmission. So it is considered safe because the encryption is based on the fact that it is difficult to get the 2' factors of a very big number. For example, this one. So if we don't know the 2' number, it will be very difficult to factor it. But Peter Shor's algorithm can factor this exponentially faster than a classical computer. So that means if a universal quantum computer is built, this Shor's algorithm can efficiently factor a big number, and this RSA encryption will be not safe anymore. So this algorithm provides exponential speedup in factoring big numbers. So this algorithm is a Guanru algorithm. So Guanru proposed it to for unstructured database search. So, for example, if we have a database and it stores color information for different boards, and we want to check which one is red. So if it's an unstructured database, using classical algorithms, we will need roughly n steps. The worst case, we will need n steps to get the answer, to get the index of the red color. But if use Guanru algorithm, so the step is only square root of n. So the Guanru algorithm makes use of the quantum parallelism. So in fact, it makes use of the superposition of the database of a quantum state. So all the information is stored in the quantum state at the same time. So one call of the function will return all the answer for the different index. So if it's green ball, the answer is 0. Red ball, the answer is 1. So that all those information will be obtained in one call of a oracle function. But it seems only one step is needed. But in fact, classical versus quantum is not n versus 1. So the steps needed is square root of n. So the steps for classical and quantum is n versus square root of n. So why it is square root of n? So we will talk about it later. So it seems it's not as good as this speedup is not as good as the Shor algorithm exponential speedup. But in fact, if n is very large, for example, if n is 1 million. Then square root of n will be only 1000. So if n is large, this speed up is still very good speed up. Quantum algorithms have many applications. For example, in material design, medicine development, logistic optimization, machine learning, AI, and investment risk management. So some of them make use of the quantum parallelism. Some of them make use of the optimization. So if a universal quantum computer can be built, our daily life will be affected, and be changed a lot. We can benefit from the quantum computer a lot, and yeah. So then, will quantum computer replace a classical computer completely? The answer is no. So the relationship between quantum computer and classical computer is like the relation between airplane and cars. Long distance transportation, we will need airplanes, and local transportation, we will need cars. So very difficult tasks will be assigned to quantum computer, and other tasks can be assigned to classical computer. So it will be a relationship of collaboration between quantum computer and the classical computer. Next is I will introduce the elements of quantum computing. First, let's take a look at quantum bits, so qubits for short. In classical computing, we have the two states of the voltage of the transistor port as one bit. In quantum computing, qubits are also two-level systems. For example, photons with two polarizations and nuclear with two spin states. So in NMR, so magnetic resonance, in nuclear magnetic resonance, qubits are nuclear spins. So they are located in magnetic field. It has spin up and spin down, two states. And these two states can be used as a qubit. So we mentioned earlier the state of quantum particles are very special. It has very special probabilities. The first is quantum superposition. So a qubit can be superpose the states of 0 and 1. So we have this mathematical representation. So A0 plus B1. A modulus square is a probability the qubit is in 0, and B modulus square is a probability the qubit is in 1. Because they are probability, the sum of them equals to 1. So for a two-qubit system, the system can be a superposition of 4 states, so 0, 0, 0, 1, 1, 0, and 1, 1. For 4-qubit system, the system can be in the superposition of totally 16 states. So it's quite different from a classical system. For a 4-bit classical system, it can only be one of the 16 base state. So this is quantum superposition. The other probability is that qubits can be entangled. So the most famous thought experiment, Schrodinger Cat Experiment. So in the thought experiment, the cat is in room where there is a radiation source. It is said this way: if the radiation happens, a bottle of poison will be broken and the cat will be poisoned and it will be dead. So if the radiation does not happen, the bottle of poison will not be broken and the cat will be alive. So the cat is in the superposed state of alive and dead. And its state is entangled with the state of the radiation state. So we can consider the cat as a qubit and the radiation source as a qubit. So entanglement is very important in quantum communication, since it's a non-local correlation between qubits. So that means if the pair of the entangled qubits are sent to different receivers, so there can be combining it with different operations. There can be information sent between the two receivers. So as we just said, the quantum states are have very special probabilities. So their mathematical expression is different from classical bit. A vector is used to express a quantum state, a qubit state. So for one qubit, the vector has two elements. For 4 qubit, the vector has 4 elements. So for n qubit, the vector will be 2 to n by 1 vector. So there's another way to express a quantum state. So its density matrix is just the vector times its own transpose. So this are the vector form and the matrix form. They are two equivalent mathematical form to express a state. So for 1 qubit, the matrix is a 2 by 2 matrix. The diagonal part is a probability of the qubit in one of the base. For example, A modulus square is the probability in 0, B modulus square is the probability in 1. So here I introduce another method to describe a qubit state, the block sphere method. So any single qubit state can be expressed as a vector in the unit sphere. So this sphere is called Bloch sphere. So the vector state, it has a direction decided by the coefficient of those superposition. So in the sphere, the north pole is 0, the south pole is 1, and all the other directions stand for a superposition of the 0 and 1. The xy projection of the vector is proportional to the off-diagonal parts of the density matrix. And the z projection of the vector is proportional to the difference in the diagonal elements. Bloch sphere, so it is very convenient to visualize single qubit gates and also decoherence. Decoherence is such a process. So it happens when a qubit interacts with its environment. So along with this interaction, so the probability of the qubit is 0 and 1. will change. And also, along with the interaction with the environment, the off-diagonal parts will get smaller and smaller. So we can visualize it in the Bloch sphere. So the projection of the vector in the xy plane will get smaller and smaller, and the projection in the z projection in the sphere will get pointing to one state, and its length get longer and longer. So decoherence means the qubit has lifetime. So after a certain amount of time, the error will happen in a qubit state. So decoherence is an important issue to overcome in quantum computing. Next is quantum gates. So in classical computing, we have different kinds of basic gates, and by composing those basic gates, we can complete different computation tasks. It's the same in quantum computation. In quantum computation, there are quantum gates. It transforms a quantum state to another state. So those two equations are the same, are equivalent. So this equation is in the vector form for the quantum states. This equation, quantum state, is expressed in matrix form. So for a n-qubit system, this vector is 2 to n by 1, and this quantum gate has a matrix form of 2 to n by 2 to n. So the evolution of quantum states obeys Schrodinger equations. So those are Schrodinger equations. From those equations, we can obtain the details of the quantum gates. With those quantum gates, single qubit gates, two qubit gates, or multiple qubit gates, we can just like classical computing, we can realize different algorithm and solve different problems in quantum computing. Single qubit gates can be visualized in Bloch spheres as rotations. For example, this rotation rotates the vector from North Pole to the XY plane. So it's like to create a superposition state starting from 0. So like this case, it rotates the vector from North Pole to South Pole. It's like to flip the bit states. And also, very complicated gates can be designed. So next is two qubit gates. The most famous two qubit quantum gates is the spin-not gate, control not gate. So control not gate, there are two qubits. One is used as the control qubit. The other is the target qubit. If the control qubit is in 0 state, there will be no operation in the target qubit. If the control qubit is in 1 state, the target qubit will be flipped. Another two qubit gate is the swap gate. Swap is a gate to switch the state between two qubits. There are also many other two qubit gates, but there is one very important theorem. So any quantum gates can be we can use quantum
Guanru, excuse me. Sorry for interrupt you. Are you listening?
We lost her connection.
Okay, we had a problem of connection. Ok, pessoal, vamos esperar um pouquinho para ver se ela torna, né? Let's wait a minute. So she had some connection problem.
Hello.
Hello again. Sorry, we had some problems on the internet, and you can return now.
Hello.
Hello, are you listening?
Hello. Sorry.
Sorry, can you hear me or not?
Yeah. So
Yeah,
where?
okay.
So where did that left? So
Okay. Uh, you
which slide?
can return because we had some problem of connection on internet. And
Oh,
okay, can you show me your slides? And
yeah.
I will point you in which point we stopped of hearing you or watching your slide.
So I cannot remember which slide. Do you remember which slide?
Okay, yeah, I can show you.
Yeah.
You can screen it.
Okay. Is this
Uh,
one?
no, before.
This one?
Yeah, that's one. No, after. Yeah, that's one. Thank you.
Okay.
Sorry for that problem. Okay.
Yes. Thank you. So here, uh, here we talked about the quantum gates. So quantum gates, using basic quantum gates, we can realize different quantum algorithms to solve different quantum problems, just like in classical computing. So single qubit gates can be visualized as rotations in the Bloch sphere. So for example, this is a rotation from North Pole to the XY plane. This can be considered as creating a superposition between 0 and 1, starting from 0 state. And this rotation, this gate, rotates the state from North Pole to South Pole. It can be considered as a bit flip operation. And also there are other, so we can design other more complicated evolution paths on the sphere. And two qubit gates. Two qubit gates, the most famous two qubit gates is maybe let me do this. The most famous two qubit gates. Sorry. What did I do? Okay. The most two famous gates is the CNOT gate. So there are two qubits. One qubit is considered as the control qubit. The other qubit is considered as a target qubit. If the control qubit is in 0 state, and there will be no operation on the target qubit. If the control qubit is in 1 state, and there will be a bit flip operation on the target qubit. Yeah. Another example is swap gate. Swap gate switch the state between two qubits. And there are also many other two qubit quantum gates. But CNOT is most famous because there is a theorem that any quantum gates can be realized by the combination of single qubit gates and the CNOT gates. So here is an example of using the 3 CNOT gate to realize a swap gate. So here I show how to use quantum gates to realize classical gates. So it should be mentioned that quantum computation falls in a catalog of reversible reversible computing. Reversible computation is a model that means the computation can be reversible in time. So usually it means the input and output, the map between input and output is a one-to-one map. So it's very apparent here that classical computation is not reversible, and its map between input and output is not one-to-one, and quantum computation is reversible. The map between input and output is one-to-one. So the Landor's principle tells us that analogical irreversible manipulation of information, such as the erasure of a bit or the merging of two computation paths, must be accompanied by a corresponding entropy increase. Specifically, in classical computation, this entropy increase is the reason for the heat dissipated by transistors. So quantum computation will not have this heating issue. So that means quantum computation is more energy efficient than classical computation. Another advantage is just what we mentioned earlier, is quantum superposition. So one qubit can be in the superposition state of 2 base, and 2 qubits can be in the superposition of the 4 base, and n qubits can be in the superposition of 2 to n base. So if we use this superposition as the input of a function, we call this function once, and we get all the results for all those 2 to n inputs. So it seems so good that one call returns all the results for 2 to n inputs. But it's not so simple. It's a bit more complicated because of the quantum measurement. Quantum measuring a quantum state will cause the system to collapse to one of the eigenstates of the measurement. So, for example, if we have such a superposition state of alive and dead, after measuring it, we will either get a result of alive or a result dead. So if we have many identical copies of this state, after measuring all of them, we will have half probability to get a live cat, and the other half is to get the dead cat. So this probability is decided by the superposition coefficient. So this means although we have this superposition state, which encodes all the function values, if we marry it, we will collapse to one base, and we will only get one result. So does this mean superposition is not useful? It is useful. So there is a subroutine called amplitude amplification. So it's a subroutine in many quantum algorithms. So if we want a correct answer, we can just amplify the amplitude of that wanted item, and shrink the other item's amplitude. So measuring the final state will return the right item with a very large probability, nearly 1. So this is also the reason that Why in Grover algorithm? So Grover algorithm versus classical search algorithm is not one step versus n step. It is square root of n step versus n step. So that's because quantum measurement will collapse the system. And to get the correct answer, we need to implement amplitude amplification square root of n times. So we get the result that Grover algorithm needs square root of n, and which is a very good speed up versus classical search algorithm. The other very important quantum task is quantum simulation. So it's one of the most important tasks that the quantum computers can outperform classical computers. So even today's most powerful classical supercomputer cannot simulate a quantum system of moderate size. So maybe 40 or 50 electrons or 40 or 50 atoms. So the degrees of freedom is much more than the classical computer can handle. So, recent years, more and more experimental work on quantum simulation has been done. This is an example. This is Google's work on simulating several hydrogen atoms in chemical reaction. Quantum simulator can be grouped to two groups. One can be named as analog quantum simulator. The other is digital quantum simulator. So the analog quantum simulator, the structure of the quantum particles resembles the quantum systems we want to simulate closely. So the structure is closely to the problem we want to simulate. That means analog quantum simulator can only simulate a type of problem. The other is the digital quantum simulator. It decomposes the simulation task to different basic gates. So that means it can realize all kinds of different simulation tasks. But this kind of simulation requires have a higher requirement for the hardware. So it requires each gate to have a very high accuracy. So this kind of simulator is still researchers are still working on this kind of simulators. But there are already a lot of experimental development on the analog quantum simulator. So next, I will introduce quickly the quantum computing platforms. This is the architecture of a classical computer. To build a quantum computer, the CPU part needs to be replaced to a quantum processing unit part. In fact, researchers are still trying to find a general architecture for quantum computers. In this talk, I will quickly introduce the most bottom part of this architecture, so the quantum chip. So I will introduce several physical platforms to realize quantum chip. They are the NMR quantum computing platform, the superconducting qubits, optical qubits, optical quantum computing. So this use photons as qubits, and ion trap and NV center in diamond. And also there are other physical systems like quantum dots. I will just introduce some of them. So the superconducting qubit system, it is the most promising system, one of the most promising quantum systems. So the qubits are the fabricated LC circuits, and its scale is in mesoscopic. It's roughly 100 micrometer. You can see the scale. For a linear LC circuit, the energy differences between all the levels are the same. So that means it's not possible to selectively control only two of the levels to use it as a qubit. So that's why Josephson junctions is included in the LC circuit. It's a nonlinear. It can be seen as a nonlinear conductor. Because of this nonlinear element, the energy level will have different differences between them. So this means it's possible to selectively control the lowest two levels and use them as a qubit. And the energy difference is usually in the frequency range of 4 to 6 gigahertz. To control them, so microwave pulses are used to control superconducting qubits, and the detection is also using microwave. Ion trap qubit system is another very promising systems. So they are ions. They are combined in free space using electromagnetic fields. So they are depending on which freedom is used. So there are different types of ion qubits. And laser and microwave can be used to control the ion qubits. And usually the detection is realized by laser and fluorescence. NV center. So NV center is so in diamond. If carbon is replaced by a nitrogen, there will be a vacancy beside it. So this is called an NV center. The electron spin state of this NV center can be used as qubit. And microwave or laser can be used to control it. And the detection is also realized by laser and the fluorescence. So this NV center system is a room temperature system. It's quite different from the previous two systems. So superconducting system need to be put in dilution fridge, and this ion trap need to be located in high vacuum, and this is the NV center at room temperature. But the problem for this system is a scalability problem. It's very difficult to get many qubits in this system. But the NV center is widely used in quantum sensing. It's a very good system. Next, I will talk about NMR quantum computing. Here are some NMR basics. So NMR, nuclear magnetic resonance. The techniques has been developed for maybe over 70 and 80 years. So the nuclear agent is a so the physics is that the nuclei with non-zero spins, they have a magnetic momentum. So they interact with the magnetic field, and the interaction causes energy level splits. So it's called diamond splitting. When a microwave field is resonant with the nuclei, if it's resonant with the two energy level, the nuclei can absorb or emit energy and transfer between the two different energy levels. The signal during this process can be collected. So NMR nowadays is widely used in in hospitals. So there are magnetic resonance imaging, so it can scan our brain. In research, university or research institute, the NMR spectrometer may be like this, and it can be used to study chemical structure of molecules. So the NMR spectrometer has such a schematic structure. So the samples are located in a coil. The samples are located in a superconducting coil. So the magnetic field, static magnetic field, is provided by the superconducting coils. Those superconducting coils are in the liquid helium environment, so the temperature is 4K. And liquid helium, outside liquid helium, there is liquid nitrogen to protect liquid helium. And to control the nuclei, users can use computer to emit microwave pulses to control the nuclei spins, and the spin signals can be picked up by amplifiers and then amplified and analyzed by a computer. Amplified and then it's transmitted to a computer and analyzed by the computer. So in NMR, qubits are the nuclear spins. So nucleus. So just now we say nuclear spin. Nuclears have momentum, have magnetic momentum. In fact, only nuclear spins with non-zero spins have magnetic momentum. So nucleus with all protons or neutrons, they have intrinsic spin angular momentum, and because they all have charge, so they have magnetic momentum. For example, isotopes of hydrogen, it has three types of hydrogen isotope, H, D, T. Their proton number are all 1, so it's odd number of protons. It has intrinsic spin. They have intrinsic spin, and the carbon-13 isotope, it has 7 neutrons, so it's odd number of neutrons. So it also has intrinsic spin. So the spin number for them are half, 1, 1, and half. So spin half, we usually use spin half as qubits. So spin magnetic momentum interact with the static magnetic field. So this interaction acts spin to process with the Lang frequency decided by gyromagnetic ratio and magnetic field. So this processing picture is more like classic picture. So to use a more quantum language, so this interaction result in Zeeman level splitting, and the 2 levels correspond to spin up. So the spin aligns more with the magnetic field, and the spin down. So the spin aligns more against the magnetic field. So these 2 states have different energy level, and the processing at Lamarck frequency, in fact, is the periodic evolution between the two states. And Lamarck frequencies of different nuclear species are quite different. For the difference of Lamarck frequencies can be made use of to address nuclear spins in control environment. For example, the hydrogen at 9.4 Tesla magnetic field has 400 megahertz frequency, and for carbon-13, the frequency is 100 megahertz. So this difference can be used to selectively control the hydrogen or selectively control the carbon-13. And a molecule with unaddressable spin halves can be used as an n-bit quantum processor. For example, this is a 3-qubit system. So, one fluorine, and one carbon-13. So all the other carbons are carbon-12, so they will not be used as qubit. They don't have spin. So this is a 2-qubit system, one hydrogen and one carbon-13. This is a 7-qubit system. It has 4 carbon-13, 2 hydrogen, and in fact, it has a methyl group. The methyl group is not a spin half, it's 3 half, it's spin 3 half, but it has a subspace of spin half. The subspace of the spin half subspace can be used as a qubit. So that means we have a 7 qubit here. Those are more examples. This is a 5-qubit system. It has 2 hydrogens, 3 fluorines. So this is a 4-qubit system, 3 fluorines and 1 carbon-13. So this carbon-12 is not a qubit. This is a 12-qubit system. The single qubit gates can be realized using RF pulses. Just as I mentioned just now, so in a magnetic field, so in this field, so this number corresponds to a 1.5 Tesla field. So this in this field, hydrogen has an energy splitting of 60 megahertz, and carbon have a energy splitting of 15 megahertz. And the frequency, microwave frequencies with 60 megahertz can be used to control hydrogen, and microwave with 15 megahertz frequency can be used to control carbon. Since the microwave has the same frequency as a spin, so it seems like they rotate around the static magnetic field with the same angular speed. So they rotate along this B0 field at the same speed. So this means if we put them in the rotating frame, which rotates around which rotate at the Lamarck frequency, then the spin will be not processing, and also the magnetic field will be like a static field in the XY plane. So usually all the information processing will be in a rotating frame. In this rotating frame, the spin is static, no processing, and the B field, the microwave field, is also static and in the XY plane. So if we apply such a microwave pulse, and the spin will rotate around this B1 field, the B1 magnetic field. So that means this microwave pulse can rotate the spin in the block sphere. It can be realized. It can be used to realize a single qubit gate. Yeah. So if by controlling the phase of the micropulse, we can realize the rotation along different axes. So we can have X rotation, and we can have Y rotation, and we can have X rotation. And by control the amplitude of the pulse, we can realize the rotation of different angles. So for example, this is a pi/2 rotation. This is a pi rotation. So X and Ly can all be realized using microwave pulses. And there is a important theorem that any single qubit gate can be realized by a series of X and Y rotations only. So that means because we can realize X and Y rotations in NMR system, so we can realize all the single qubit gates in NMR system. So 2-qubit gate in NMR. The 2-qubit gate in NMR are realized by the J coupling. So because it's a 2-qubit gate, that means the 2-qubit need to interact with each other. So this interaction, so in NMR, this interaction, we can use J coupling as this interaction. So J coupling is such a coupling interaction mediated by chemical bonds. So the 2-qubits, they share electron pairs between them. So this coupling is mediated by such electron pairs. So with such couplings, we can realize such 2-qubit gates. So to realize C0 gate, we need to combine the single qubit rotation gates and also the J coupling evolution gates. So this is the sequence to realize the C0 gate. So I want to remind you the important theorem that any quantum gates can be realized by the combination of a single qubit gate and the C0 gate. So this means in our NMR systems, universal quantum computing gates, so a universal set of quantum computing gates can be realized. So here is another sample. So this is a 12-qubit system. So we have 7 carbon-13 and 5 hydrogen. The diagonal part are the frequency offset for each qubit, and off-diagonal part are the J coupling values between them. So it can be seen that the nearest neighbors have largest coupling. So we do hope the coupling are large enough so we can have fast enough 2-qubit gates. Next is the state initialization in NMR. So proper initial states is required for computation, so such as 0, 0, 0, so all 0 for all the qubits. But in NMR, we have usually we have a lot of spins. We have a lot of copies of the quantum system in our NMR ensemble. It's usually 10 to 19 or 10 to 20, something like that. The number is very large. And all the spin ensembles is subject to Boltzmann distribution when they are in the thermal equilibrium state. So such state, the circle equilibrium state, the density matrix can be written as a sum of 2 parts. The one part is identity, the other part is a non-identity part. So I give a very easy, very simple example here. So for 2-qubit system, we have 4 energy levels: 0, 0, 1, 1, 0, and 1, 1. So 4 energy levels, there will be different occupations because of the follows Boltzmann distribution. So in the density matrix, the large identity part will not generate any signal in NMR spectroscopy. Only this non-identity part can generate signals. So this part is called polarization. But this part is very small. It's 10 to minus 5. So this equilibrium state is a mixed state. To do quantum computing, so researchers propose to use pseudo-pure state in NMR. So this kind of state is a sum of identity and skewed pure state. So such a state has same unitary dynamics and observable effects as 0, 0, 0. So it's used as the initial state in quantum computing. This is a very simple image to prepare a pseudo-pure state. We start from a thermal equilibrium state and prepare it to be in such a state. All the other energy levels have the same property distribution, the same number of molecule spins, and only this energy level has a different number of spins. So this amount of difference is used as the initial state. So this is called a pseudo-pure state because it's not a real pure state, not a real pure state. Another thing that I should mention here is the measurement in NMR. So because we have so many copies, so it's a bit different than the measurement I mentioned earlier. So earlier I mentioned that in quantum physics, measuring a quantum system, the state will collapse to one base of the system. And after measuring many copies of this system, we can get a probability of each state. So this probability is decided by the coefficient of the superposition. But in NMR, because we have the sample is already an ensemble, so it includes many copies already. So one measurement is the measurement on all the copies in the NMR sample. So that means we can get such kind of probability faster than on the single quantum system, the single copy system. So in NMR signals are called FIT signal. This signal is proportional to some coefficients of the density matrix of the states. So by measuring the different coefficient of the density matrix, we can reconstruct the density matrix of the state, and thus we can reconstruct the quantum state. There are many algorithms already realized on quantum computing, quantum NMR quantum platform. So those are very limited examples. The earliest quantum algorithm realization, such as realization of Guanru algorithm and realization of Peter Shor algorithm, they were all on NMR quantum platform. And then nowadays, researchers are still working on quantum simulations using NMR quantum platform. And there are many other examples I just I just listed very limited examples. So next, I will introduce products of my company. So SpinQ is an outstanding innovation representative in the field of quantum computing in China. So we are committing to the commercialization of quantum computing. Our team has a broad mathematics background and also an industry background. So those are our products. So it mainly includes 3 types. The first is the desktop NMR series, the Gemini, Gemini Mini, and the Triangulum. So Gemini and Gemini Mini both accommodate a 2-qubit system. The Triangulum has 3 qubits. The desktop series highlights features such as small volume, lightweight, low cost, and maintenance-free. They also have very user-friendly software interface and designed for quantum computing implementation. And also there are some very famous algorithms built in as learning examples, such as Guanru algorithm. The desktop NMR series aim at quantum computing education and teaching. I would like to highlight Gemini Mini. It's a simplified version of Gemini, and it's very small. It's only 30 centimeters in dimension, and it is only 15 kilograms. Besides, it has a very low price point, only about $5,000. So we believe it is more affordable for most K-12 schools around the world than Gemini and Triangulum. The second product is a Taurus Quantum Computing Cloud. So it provides users with access to multiple quantum computing physical systems, including superconducting qubit system and NMR systems. And the other type of product is the superconducting qubits products, so including the F control and the measurement system, and also the superconducting quantum chip. We are building our own clean room for superconducting chip fabrication. Our topic today is the NMR desktop system. So NMR desktop systems are our most material products. But before go to more details, I would want to let's take a look at comparison between our desktop and our superconducting qubit system. So the desktop works at room temperature, and while the superconducting qubit system works at 10 millikelvin. So dilution free is needed for it to work. So our desktop is maintenance free, but it only has 3 qubits. So the superconducting chip systems, because there's dilution free and all the microwave control electronics, so it requires professional operator. So it aims more at research and more at the research side. And these qubits doubles, so our plan is to double the qubit number every year. So why did we choose NMR system as a desktop system? So there are several reasons. So first is NMR techniques has been developed for over 70 years. So the F control techniques are well developed, especially the NMR system is the first physical platform that was used for quantum computation. There are, just as I mentioned earlier, that many quantum algorithms were first demonstrated in NMR systems. And the quantum control techniques developed in NMR system are also borrowed by other quantum computing systems, such as superconducting qubit systems. Second, NMR system can be made very small because the development of this material. So this means we can make the magnets very small, and also we don't need any cooling system. It works at room temperature. That means it's maintenance free and it's at low cost. So despite this limitation, the NMR systems, quantum computing systems, has a limitation of scalability. So despite this limitation, so NMR system is an ideal candidate for portable quantum computing platforms aimed at education. Here I list a comparison between our NMR desktop and other high field NMR spectrometers. So usually the high field spectrometers, they are very high, sometimes can be as high as 3 meters. And our desktop are only a few tens of centimeters. Mini is only 30 centimeters. So the large spectrometers require regular refills of liquid helium and liquid nitrogen. So they need to be located in very special labs. Besides, they are very expensive, on the order of $1 million US. They are not really affordable for personal use. But our desktop are very small and light. They don't require liquid helium and liquid nitrogen refills, and they are cost effective. The Mini is only 30 centimeters. And it's only so it only costs several thousand US. To achieve those advantages, we also need to make some compromises. For example, it's very difficult to reach a high magnetic field, and also the fielding homogeneity is a bit worse in our desktops. So in spite of those drawbacks, we already achieved a very good control quality. So quantum algorithm demonstration and some research can also be realized using our desktops. This is the 2-qubit Gemini structure and the molecule used here. We use phosphorus and hydrogen as a 2-qubit system. Those are the spectrum, the spectra of the 2 qubits. In fact, there are also 6 hydrogen spins that they are very far away from the phosphorus spin. So those hydrogen spins only weakly interact with the phosphorus, so we ignore the effect of them. We only consider it as a 2-qubit system. So this molecule is located in the middle of the permanent magnets, and there are 2 RF channels, microwave channels. One is used to control hydrogen, the other is used to control, both control and detect the signal. So one is for hydrogen, one is for phosphorus. And there is also a temperature control unit, because the permanent magnets are very sensitive to temperature. If temperature is not stable, the magnetic field is not stable as well. And all those controls are realized using a master board, and the master board is connected to a PC. On the PC, the SpinQ software is installed. SpinQ is a user-friendly interface to use our quantum computer. So it has different modules. So one module is a quantum computing module. The other is a nuclear magnetic resonance module. So in this module, users can have access to NMR signals of hydrogen and phosphorus. Also, users can adjust the control pulses for the two qubits. So this is a very good example of modern fast Fourier transform-based NMR spectrometer. In the quantum computing model, we have all the basic gates required for 2-qubit quantum computing, and also user can compose their own circuit, and also we have built-in algorithms. So the user can compose the circuit using a drag and drop fashion. And under the circuit, those are the pulse sequence that correspond to all those basic gates. The results are returned in form of density matrix. So that there are two types of density matrix here. So one is the simulation result. So there is a built-in simulator in this software. So this is an experimental result. Here I give more details for the available quantum gates. So all the X, Y, Z rotation gates and arbitrary angle rotation gates, and also the two-qubit CNOT gates. All the single qubit gates are realized by square pulses. And the CNOT gates are realized by combination of the single qubit gates and the J-coupling evolution. And yes, this is the state initialization. So just now I introduced that in NMR quantum computing, pseudo-pure states, PPS state, are used as the initial states. So we use a method of relaxation method to realize such a PPS state. So it's a repetition of this sequence for many times. So the idea is to permute the three level, permute them and let them relax. Relax, if you remember, relaxation, T1 relaxation will change the probability distribution among those space. But because we are permutation, yeah, we are permuting these three states, so they tend to have same probability, and while the other one will have very different probability. So this will be used as an initial state. And yeah, we do quantum state tomography to collect to get the final state information. So this is an example of a Guanru algorithm. So it's a built-in algorithm in the 2-qubit software, but also users can compose by themselves. So this is an example how to get the built-in experiment. We have built-in experiment of Bell state preparation, Guanru algorithm, Dodge algorithm. And also users can compose their own circuit. So CNOT different 2-qubit gates and Hadamard gates And so X gate is a bit flip gate. And the corresponding pulse sequence will be shown under below the circuit. This is the Gemini Mini. So this is relatively new product. So it launched earlier this year. It's much smaller and lighter because we have used a smaller magnet, and the volume is smaller, and also the magnet provides a smaller magnetic field. So the magnetic field is about 0.5 Tesla. Yeah, I don't remember. Yeah. The field homogeneity is a bit worse than Gemini, and the pulse length is relatively longer than Gemini as well. So these two specs are not as good as Gemini, but the Gemini Mini, the control in Gemini Mini can already achieve a Gruber algorithm fidelity of higher than 80%. So this one is very good for learning or for teaching or learning basics of quantum information. Next is the 3-qubit system Triangulum. So this is a molecule used in this system. It has 3 fluorines at the 3 qubits. The structure is similar to Gemini's structure, but there are several important differences. So first, we add a field locking system. So this system is to feedback, use the spin signal of the hydrogen spin signal of acetone to feedback the field strength. So we detect the field, the frequency for the hydrogen, and we can detect from the detected frequency. We know how the field drifts, and we can compensate the drift. So this way, we make the field strength more stable. The other important difference between Gemini and Triangulum is that Triangulum provides the arbitrary waveform generation function. So this function, because we need to control the 3 fluorines at 3 different qubits, single square pulses cannot realize such kind of control. So we need to design very special pulse shape to individually control the 3 fluorines. So the arbitrary waveform generation function is for this reason. So we can design shapes which has very narrow frequency selection profile. So, for example, one pulse is can be used to selectively control this fluorine. Another pulse for this one, another pulse for this one. If we simply use square, we always control the 3 fluorines at the same time. So that's not what we want. And the arbitrary waveform generation function is very powerful. And advanced users can design their own pulse shapes as well. Yeah, next is the SpinQ interface for Triangulum. It's different. Here we don't have the pulse sequence shown here because every pulse has its own shape. It's very complicated pulse shapes, so we don't show here. And also the return result is a bit different from the 2-qubit case. The full density matrix is not returned. Only the diagonal parts is returned. So that means only the probability on different base are returned. So it's because a 3-qubit density matrix reconstruction takes a very long time. So we didn't make this function as a built-in function, but advanced users can reconstruct the full density matrix by their own. So those are the available gates. So I will not go to details of the different gates, but it should be mentioned that all the single qubit gates are realized with special design shapes. So for state initialization, we also use pseudo-pair states, but only difference between this case and the Gemini is that the permutation gates is realized by a special shape, not the sequence of square pulses. Here is a Guanru algorithm in the SpinQ software of Triangulum. And this is a show of how to compose circuits. So all always say our desktops are aimed at quantum education and teaching. In fact, we have tried more advanced algorithms on our desktops. So for example, we realized the Vqa algorithm. So it's a class of algorithms under the hybrid quantum classical framework. So in this algorithm, part of the task is assigned to quantum computer. The easier part is assigned to classical computer. So it uses a parameterized quantum circuit to estimate the cost function and use a classical optimizer to optimize the cost function. VQE is a type of VQA algorithm. So VQE aims to find the ground state of a given Hamiltonian. So the algorithm we realized is a VQE, and the quantum circuit. So we parameterize the quantum state using quantum gates, and there is a parameter in the quantum gates. So by checking this parameter and realize different quantum states, and we can measure the expected value of the energy and use the gradient or gradient-free method to minimize the energy. So using this way, we can get ground state energy estimation of a Hamiltonian. So this is a Hamiltonian. We try to find the eigenstate and energy. We try to find the energy of this Hamiltonian. This is the circuit we use to realize the quantum state, and we use the gradient method. So this is the experimental procedure. So this Hamiltonian has a ground state energy of -3. So the red lines are the theoretical predictions. So we realized this algorithm on our Gemini and also on the IBM-Q Yorktown. So we use the 2 qubits of the IBM-Q. So they have quite similar result. So after error mitigation, the experimental result is -2.98. So it's very close to the theoretical value. And the difference between so the performance of our Gemini is similar to the IBM-Q Yorktown, the first two qubits of IBM-Q Yorktown. But the difference is that in our case, our error comes from the T2 star error, and the error in IBM-Q Yorktown comes from the measurement error. We implemented another algorithm than on Triangulum. So it's the HHL linear equations, so solving linear systems of equations algorithm. So HHL algorithm has become a subroutine in many quantum algorithms. So because we only have a three qubit system, we realized a simplified version of it. And this is a result. We repeated the experiment 5 times, and we get the so the average of the result is very close to the theoretical value. So this means the successful realization of complex algorithms on Gemini and Triangulum means that researchers can also do research on such desktops. So our products have been sold to many places, and we are also developing new desktops. We are developing Triangular Mini and also a 5-qubit system. Also, our software team is working on the SpinQ Kit. It's a quantum computing development platform. We are also working on superconducting chip and the RF measurement and control system, plus dilution refrigerator. Thanks to our team, because of their hard work, we now have very good desktop system, and also we are making progress in the superconducting qubit system. For summary, so quantum computing will bring revolutions in science, technology, economy, and our everyday life. And important quantum resources, so superposition and entanglement. The platforms, NMR, so this is very good platform for desktops and superconducting qubits and trap and vCenter, etc. And the most mature product of our company is SpinQ Desktop, Gemini Mini, and Triangulum. Okay, thank you.
Oh, okay, Guanru, thank you for your very nice presentation. Okay, now you are waiting people in chat asking or if you have questions. Meanwhile, I have some questions. Okay. My question is, when you compare, it's not clear to me. Okay, when you compare Gemini and Gemini Mini, both have 2 qubits. However, one is much cheaper than the other. What's the basic difference?
The most important difference is the control accuracy of Gemini is better than Gemini Mini. So in Gemini Mini, we have weaker magnetic field. So weaker magnetic field means lower frequency for the 2 qubits, and also we have longer control pulse for the 2 qubits in Gemini Mini.
Okay. Everyone, sorry, we have some problems right now. Please stay here.
We lost her connection. Oh, he's on again.
Okay. Okay, Guru, we're back again.
Yeah. So also the weaker magnetic field and a little bit worse homogeneity for Gemini Mini, so the longer control process for Gemini Mini all contribute a little worse control fidelity for Gemini Mini. But for simple algorithms of shadow depth, Gemini Mini still have a good, we say good enough fidelity. For example, for root algorithm of 2 qubits, it can have 80 fidelity, but for Gemini, it can
Guanru, sorry interrupt you because the sound is not good here. It's a bit digitalized. I mean, can you repeat? Okay, it's not good yet. We are having the same issue of connection. Okay, please repeat some part of our explanation.
I don't know.
Okay, the sound is not good. I don't know what to do. Sorry. Evandro, do you have an idea?
Oh, I don't have any idea. It's a connection, I believe. No, it's still robotic.
Okay, well, please try again. Let's continue.
Eduardo, try removing your webcam.
Okay, sorry. Okay, please, can you speak, Guru? Oh, okay, it's the same issue. Okay. I am not sure if people are listening, are understanding. Probably not. So I don't know what to do. If you interrupt it right now, or if you continue.
Guru, you can try to connect with your smartphone. Maybe. Eduardo, I believe you can share your webcam. It's not related to a version.
Yeah.
Então vamos esperar só um minutinho, acho que ela deve estar conectando de volta com o celular. Acredito que, como não tem que mais compartilhar, a apresentação seja melhor.
Okay. Pessoal que está ouvindo a gente pode botar perguntas, se tem alguma dúvida, pode colocar em português mesmo. A gente faz a pergunta e se precisar fazer alguma interação. Ru? Hello?
Yeah.
The sound isn't good. Again, I don't know, maybe.
Hello?
Yes, isn't good, the connection.
Hello?
It's not
I believe
good.
that now it's okay.
It's okay.
Guru, can you speak something so we can check? Oh.
Is it okay now?
Okay. Yeah. It's much better now. Thank you. Sorry for that. Okay, could you restart the explanation? Not totally, but part of it.
Okay. Yeah. So the Gemini Mini to the field strength and also the field homogeneity is worse than Gemini, and so also the house length to control qubits is longer than Gemini. So both all those points contribute a little worse control fidelity for Gemini Mini. So for Gemini Mini, the control fidelity is a little bit worse, but it's good enough to on Gemini Mini. So quantum algorithms of shallow depths can be realized with a relatively good fidelity. For example, Guanru algorithm on Gemini Mini, the final fidelity is roughly 80%. But on Gemini, we can have a higher fidelity for algorithms such as Guanru. We can have a better fidelity than 90% on Gemini, so 90% or more on Gemini. But Gemini Mini is only around 80% fidelity. So Gemini Mini is more for basic knowledge learning and basic, very simple algorithm demonstration, aimed for starting who just start to learn quantum computation. Gemini, so I showed a complex algorithm demonstrated on Gemini in the slides. So it's a VQA. So the successful realization of the complex algorithm means that on Gemini, some scientific research can be done on Gemini. So the price is mainly about the control fidelity part.
Okay. Okay, thank you. I understood now. I have another question related to the temperature. Gemini and Gemini Mini, they work at room temperature. However, when you start talking about nuclear magnetic resonance, you mentioned a refrigeration, a cooling apparatus in which the system works at 4 Kelvin. Why these two quantum computers, Gemini and Gemini Mini, they don't need this cooling process? Is a molecule that's different? What's the difference?
Oh, the reason is for the large NMR spectrometer, for those ones, so the magnetic field of those spectrometers are very high. So for example, maybe around 10 Tesla. So in order to get such a high magnetic field, they use the superconducting coil to generate such high field. So to maintain a superconducting state, the coil need to be placed in the liquid helium, and so it requires a 4K environment. But the molecule does not require such environment.
Okay.
Our desktop, we don't need such a superconducting coil. We use permanent magnets, but the drawbacks is that we cannot reach such high field. Our field is only around 1 Tesla for Gemini and Triangulum. For Gemini Mini, the field is lower, around 0.5 Tesla.
Okay, thank you. I understand now the role played by the helium, the liquid helium. Okay, thank you. There is a question from Eduardo Lucy. Can Gemini be used for quantum control studies?
Quantum control, sorry, what's the last word?
Studies.
Oh, yes, it can be used for quantum control studies. So, quantum, I mean Gemini. So in Gemini, we don't have the arbitrary waveform generation. So all the quantum control is realized using square pulses. I would say a limit types. Hello, yeah, can you hear me?
Yeah, I hear it.
So limited types of research of quantum control research can be done on Gemini. So those research can only use square pulses. But on Triangulum, we have the arbitrary waveform generation function, so the user can design their own pulse shapes. So users have more freedom for quantum control study.
Okay, thank you. Very nice. I'd like to know if people are listening and watching us have more questions. Please write in the chat. No. Okay, I have a general question related to SpinQ company. What are the skills someone must have to work on SpinQ?
Oh, sorry. Can you repeat the question?
Oh, yeah. Okay. What are the skills someone must have to work on SpinQ?
I expected. Sorry.
For instance, okay, here we have a lot of students. They sometimes suppose that they want to work on SpinQ, okay, find a job there. And what are the skills they must have? I mean, they must know quantum algorithms, or the basis of quantum computation, or more advanced levels of quantum control techniques. What kind of disability?
Oh, skills. Oh, I see. I think quantum control and quantum algorithm and so maybe if superconducting, I think superconducting qubits, knowledge of superconducting qubits will be very welcome. So skills in superconducting qubits control or simulation, yeah, will be very welcome.
Okay. Simulation. Thank you. There is another question here. Thales Argolo Jesus is asking if is any optimal control technique or strategy used in such computers?
Yes. In fact, in Triangulum, so the 3-qubit system, we already implemented the great pulse engineering. So great pulse engineering is a gradient ascent pulse engineering technique. It's an optimum control pulse optimum control techniques. So using that algorithm, we design special shapes to realize different kinds of gates on the 3-qubit system, including single qubit gates and multiple qubit gates. We also use other techniques such as strong modulated pulse engineering on Gemini Mini. Because the Gemini Mini, it has limited control freedom and limited control quality. So we will currently we have been making use of the strong modulated pulse sequence to improve the control fidelity. We already had some improvement in Gemini Mini's control quality.
Okay, very nice. No more question. Okay, Guanru, I'd like to thank you again for your very nice presentation. Sorry for that internet kind of issues related to connection. It's quite common. Sorry, it's out of our control. Okay, but we are very happy for a very nice presentation. Thank you again.
Thank you very much for the invitation. It's a great pleasure to present here.
Okay, very nice. Okay, so thank you for everyone that was watching us, and bye bye. See you later when you end the hackathon at late. Okay, bye bye.
Okay, bye.